Tamamdır. Record'da başlatmış olduk. Alright, so let's start with a brief summary of what we have done in the previous lecture. In the previous lecture, we defined non-linear spaces. So what was the main definition that we introduced in our vector space by defining norms? It is the concept of a distance, right? So the norm of two vectors is basically the distance between those two vectors. And the norm of any single vector is the distance of that vector to the origin of the vector space. So the norm functions will be important for building up this geometry in our vector space, and it needs to satisfy certain properties such that it has to satisfy the triangular inequality, and the scalar multiplication should satisfy certain properties, and also the norm should return. Norm function should get non-negative values. So and those values should be equal to 0 if and only if the input to that norm function, I mean the x, is equal to 0. So that was the main definition we talked in the previous lecture, and we saw some examples, and with those child examples we tried to show that the axioms of norm are satisfied for some functions. We also see some counter examples. Maybe we'll come to that later. At a certain stage, we also defined p norm. So we said that, okay, the p norm can be defined as follows. Also the norms that we have seen before, L1 norm, L2 norm, L infinity norm, can be all put into the same picture by defining the p norm over there. And but later on we also see that, for example, if we use the p norm definition for p values less than 1, then we saw that the resulting function does not satisfy the axioms of norms, right? So actually this p norm is defined, maybe I can write more explicitly, for p values greater than or equal to 1, where p is a real number, okay? And we also talk about the fact that as p goes to infinity, the definition of the p norm turns into this maximum of the absolute value of the entries definition. We said that they're equivalent as p goes to infinity. And we also try to plot the unit spheres with respect, which are defined with respect different norms. L1 norm, L2 norm, L infinity norm, etc. By the way, we said that this is a sphere, but here there's a typo in the sense that, so this is a sphere when it is equal to R. So maybe I can do like this. Let's see. So when this is equal to, so the distance of the points to a certain center is, if it's equal to a certain value, then we are talking about the surface of a ball, then it is called the sphere. So ya da şöyle yazayım, belki daha net olur. So we use another color to make it simple. Şöyle gidersek eğer. So if we say equal, then it is a sphere. If you say they're less than or equal to R, then it is called a ball, okay? As a matter of fact, if it is less than R, then it is called the open ball. If it is less than or equal to, then it is called closed ball, etc. Anyway, so we said that, okay, let's try to plot these spheres for different values of p norms. And I showed you another animation on the slides, and we were able to plot those unit spheres. Okay, and then we said that, okay, so another important vector space that we will consider throughout the course is the function spaces, and said that, okay, if we can have some functions with properties that's such that their absolute value and p power are integrable, I mean, they're bounded there. Then we can define L1 norms, L2 norms, L infinity norms, etc. And I also just before this lecture, I was plotting if this is the f function, the infinity norm is actually the maximum value of that function in its absolute value, taking within the defined interval. Okay. And one of your friends just asked, so if those intervals has to be defined between 0 and 1? No, as long as they are integrable, we can define the corresponding norms accordingly. So there's no problem for us. But they should be, and their norm should be bounded for sure. And another important vector space that we are considering frequently is the matrices. And now we will be talking about the matrix norms. So let's start that. Okay, so the first thing that I would like to start with that is that we can define norms matrix by using different approaches. So let's start from one of them, and then we will proceed one by one how it goes. All right, so here's given one definition. It says that let V be the n by n real matrices, and this notation actually corresponds to the whole matrix A here by referring to its entries, ijth entries. And it says that the norm of the matrix m by m matrix A is defined as the maximum value of the absolute value of its entries. So let's try to see that if that satisfies the axioms of norm. Okay, so let's write down the axioms of norms. Maybe I can change color to once again blue. There. All right, so in order to show that that definition satisfies the axioms of norms, we need to show first that the definition satisfies the triangle inequality, right? It says that this should be less than or equal to norm A plus norm B. So according to this definition, what is norm A plus B? That is equal to, so A plus B is going to be another matrix whose entries are going to be Aij, Bij, and I will get the maximum of that guy, absolute value of Aij, Bij, right? And by using the definition of the absolute value function, I can say that this is less than or equal to the maximum value of the individual terms over here, Aij plus Bij. So I compute the max over there. And if I'm maximizing those terms, the sum of those terms over the indices Aij, this is also less than maximization of the individual terms. So let's say max Ij, Aij plus maximum of J, B, J. And as you saw already, I guess that we were able to change the color here. So this has now became the definition of norm of A, and this became the definition of norm of B. So we were able to show that this is less than norm A plus norm B. I mean, norm A plus B is less than norm A plus norm B. So the first thing that we need to show is shown. Let's try to show the remaining ones. What is the second axiom? It's about scalar multiplication. Okay, so we were saying that norm of alpha times A should satisfy the absolute value property. So let's have a look at that. So according to the definition, the norm of alpha times A is basically max ij. Alpha times A is going to be another matrix where each entry is multiplied by scalar value alpha. So it's going to be equal to each entry A ij like this. And since that alpha is not changing with the ij indices, I can write that thing as absolute value of alpha times maximum value of ij, absolute value of aij, and that is simply equal to absolute value of alpha times a. Okay, so that is also satisfied. And the third property was norm of A being equal to 0 means A is equal to 0. But it is, if it was an if and only if condition, right? So we need to show that property in both directions, both in the forward direction and both in the reverse direction. Okay. So first, if norm of A is equal to 0, then this dictates that the maximum value of this absolute value of its entries is equal to 0. Okay. And if the maximum value of the absolute value of things are equal to 0, so it's so these are all positive numbers, non-negative numbers, and the maximum value of those non-negative numbers is equal to 0, which means that those numbers are equal to 0. So I can say that aij's are equal to 0 for all ij, and that means the A matrix is equal to 0. And we also need to show that if A matrix is the 0 matrix, then its norm that according to that definition should be equal to 0. So if we look at this n by m 0 matrix, if we apply the norm definition, so the max ij, absolute value of aij is going to be max ij, absolute value of 0, and that will be simply equal to 0. And I can conclude that norm of 0 n by m matrix is equal to 0. So those two are also checked. We show that in both directions. Then we basically show that by using this norm definition, the maximum value of the absolute value of elements, I can define a norm on the m by n real matrices. Okay.
Hocam bir şey sorabilir miyim? Burada P1'de ilk küçük eşittir değil de bir sonrakinde. Orada eşitlik mi olması gerekiyordu? Küçük eşitlik.
Not really actually. So we are tracing over a sum of two terms, right? And we are trying to find the index that brings us the maximum value of the sum of two terms, okay? So this is smaller than the maximum value of individual terms. Do you see what I mean?
Tamam hocam, teşekkürler.
Okay, good question. And all right, here comes another definition, and it says that once again we consider the n by m real matrices, and it says that the norm of A can be defined as, in another definition, the maximum value of the absolute sum of rows. By the way, And this is from J from 1 to M. So 1 second. Maybe I can write it with a red color. So this should be M. There's a typo here. So you can also correct in your notes. So we are traversing each row of the matrix and we are summing over the columns. So, and we are checking the absolute value of absolute sum of the rows. Or maybe I can write down the example to make it more evident. So let A be equal to 2 minus 2, 1, 3, minus 1, minus 1. So we will compute the absolute value of sum of absolute value of the rows. Okay, so it will be simply equal to, let's say, okay. Then norm A is equal to maximum of the absolute sum of the first row is like 2, 1, 1. Simply equal to 4, and the sum of the absolute value of the second row is like 2, 5, 6. So that's the second row, and this is equal to 6. And as an exercise, you can show that this definition satisfies the axioms of norms. Okay. So the next thing we will do is that, as I said before, there are different ways to define matrix norms, and one way is to treat the matrix just like a vector. So, we will unwrap the elements of the matrix into a vector, and then apply the norm definitions that we used for the vectors. So let me show you an example. So suppose A is equal to 1, minus 2, 3, minus 4. Okay. And then we will put those numbers into a vector and treat that thing as a vector. Okay, so let's say I write these things again as A is equal to 1, minus 2, 3, and minus 4. And now that I put that into vector, I have this infinite norm, L1 norm, L2 norm, LP norm, etc. I can use all these definitions to define the norm of matrix A, okay? And if I do that, for example, the infinite norm of that matrix is going to be what? The maximum value of absolute value of these entries, right? And so it is equal to, it's going to be equal to 4, right? And the L1 norm is going to be equal to, so not infinity, but 1. Let's see. So that's going to be the sum of absolute value of its elements, right? So it's going to be 1 plus 2, 3 plus 3, 6 plus 4 is going to be 10. So if we show once again the A matrix by its entries, so and the infinite norm of A is simply going to be the maximum value of its entries, Aij, right? And L1 norm of that matrix is going to be summation over I and J, absolute value of Aij. And similarly, you can define LP norm and L2 norm. So let's try to write down L2 norm, okay? So that will be equal to summation I and summation J, absolute value of Aij squared, the power 1/2. There's a more compact way of writing this. So something maybe I've seen this before. It can be also written as trace of A transpose A, so square root to the power of 1/2. By the way, it is, you can also show that this definition is equal to that definition, okay? Some of the individual terms, or you can verify that, right? So yeah, try to show you on a 2x2 matrix, so let A be equal to A11, A12, A21, A22. Then the trace of a matrix A is the sum of its diagonal elements, okay? So then trace operator is simply equal to A11 plus A22, okay? So the definition claims that, so you will work with A transpose A. So let's write down A transpose as well. So A transpose is simply equal to A11 is 2 by 0, which A21, A12, A22. And A transpose A is equal to, say, it's going to be multiplication of those two matrices, A11, A21, A12, A22, times A itself, A11, A12, A21, A22, okay. And that 2 by 2 matrix multiplied by another 2 by 2 matrix is going to be another 2 by 2 matrix, right? And let's try to compute the elements at the diagonal, because the trace operator sums up the diagonals, right? So the first element of the diagonal is going to be the multiplication of this guy with that guy, right? So I can get rid of those. So it's going to be simply equal to A11 square plus A21 square. And if you compute the second element, second diagonal, it's going to be the multiplication of those second rows and second columns. So that will be equal to what, A12 square, A12 square plus A22 square. And this was A transpose A. And I didn't compute those values because I don't need that to compute its trace. Trace of A transpose A is equal to A11 square plus A12 square plus A21 square plus A22 square. And two norm of matrix is then equal to trace of A transpose A in square roots. And this is also called, is known as the Frobenius norm. So it might be good to play around with these matrix manipulations to end up with this such compact terms. Okay, so there's another there's another way of constructing matrix norms, and that will appear as the induced norm of the matrices. But before going to that definition, do you have any questions? So once again, there are multiple ways to define norms of matrices. So we see some definitions, and then we saw that one way is to treat the matrix as if a vector and use the vector norm definitions on that matrix. And the third way to construct norms is by defining induced norms on the matrices.
Hocam,
Buyurun.
burada bir matrix veriyor ve işte bir de norm tanımı yapıyor ve bunun işte norm mu değil mi diye bakın deminki örnek gibi aslında öyle sorduğunda o zaman biz direkt mesela vektöre çevirip öyle de deneyebiliriz değil mi?
For the first example, for example, you have to treat it themselves, right? So if that is possible, for example, in this example, when we're talking about absolute sum of rows, then you need to do something else, right? So absolute maximum value of absolute sum of rows does not correspond to this vectorial definition. So that was another way of defining norms, right? So you need to show that definition satisfies the axioms of norm separately, just like we did over here. So this is another family of norms defined on matrices. Is that okay?
Evet hocam.
Yani sadece ona geçerekten olmuyor. Başka tanımlar da var. Onlar da sağlıyor mu diye ayrıca kontrol etmek lazım. Definition'ları teker teker. Alright, so another important definition for constructing norms of matrices is that the concept of an induced norm. And the idea is that, okay, I would like to define a norm on the matrices, and I still want to use the norm definitions on the vector spaces, okay? So it says that RA be a m by n matrix, and suppose that we are given two vectorial norms, which is defined on Rn, the other one is defined on Rm, okay? So these norms denote the norms, vector norms basically, for the n-dimensional and m-dimensional real vectors. Okay, then the induced norm of a matrix is defined as, so you can take the norm A as you compute the maximum of, so you try all these x vectors possible except for x equals 0, and you want to maximize a ratio, and the ratio of two norms actually, and the ratio of the norm of A times x is going to be a m-dimensional vectors divided by the norm of x itself. Okay, so it's an n-dimensional vector. So this is called induced norm because now I'm using on numerator and denominator those vector norms. Okay, so this is a matrix norm induced by the vector norm. So maybe I can write it down more explicitly. So when I say the induced norm over here, I mean that this is a matrix norm induced or constructed, let's say constructed or induced by using the definitions of vector norms in Rn and Rm. All right, so we will see examples about that will be more clear. So the first that definition is going to look like alien, but later on we will be more comfortable with that. So the induced norm of the matrix can also be defined in another way. So that I will give you another definition. And so let me write that thing once again, maybe more explicitly. So I will write this as Rn, and this is the norm in Rn. Okay. And what I would like to emphasize is that so I can write this the same thing over here as norm Ax divided by norm x as. So since the norm of a function is going to be a non-negative scalar, and if x is different than 0, it's going to be a positive number, it's positive scalar. So I can write that thing as norm of Ax divided by norm x. And if you just look at the second term over here, this guy over here, so this is a normalized vector. I mean, if you divide the vector with a scalar where the scalar is equal to the norm of that vector, so this is a vector with unit norm, right? So this is a vector with unit norm. So therefore, instead of maximizing the Ax divided by norm x over all x, I can maximize the multiplication of A and x where the norm of x is equal to 1. So among the all unit norm matrices, I am looking vectors, sorry, I'm looking the maximum norm of Ax. I can also write that thing more explicitly. So what I in that transition, what I'm trying to say is basically this. So I can write norm of x divided by alpha. This can be written as norm of x divided by alpha if alpha is greater than 0. That's what I'm saying. So now we have two equivalent definitions. You either consider all x's in the n-dimensional vector space except for the 0 vector, and try to maximize the ratio of Ax divided by norm of x, or you fix the norm of x to be equal to 1, okay, and maximize A times x by considering all the unit vectors in Rn which has the norm equal to 1. These are the unit vectors that we showed by plotting the unit spheres in our previous lecture. So these two definitions are equivalent, and we will use both of them. Okay. Do you have any questions? Anything I can explain better?
Hocam ben sadece şurada x'in normuna alfa dedik ya hani.
Bu alfa herhangi bir non-negatif sayı olsun dedik. Hatta pozitif bir sayı olsun dedik yani. Sıfırdan farklı olacağı için.
Yani bizim durumumuzda onu sağlıyor mu x'in
Evet.
normu?
Tabii normun tanımı neydi? Herhangi bir vektörü alıyordu. Non-negatif bir sayıya map ediyordu. Hatırlıyor musunuz norm definition'ını?
Evet. Peki ben mesela pay kısmındaki
Şu yani
şeyde niye
norm,
olmuyor?
norm x her zaman böyle yani.
Peki pay kısmında bulunan a çarpı x hani matris çarpı vektör. Onu neden direkt mesela hani alfa gibi alamıyoruz?
O da bir vektör ya, hani şu bir vektör alfa. Şu normunu alfa gibi alabilirsiniz. Beta gibi alabilirsiniz hani yani. Şu bölümün hani bir beta bölü alfa gibi bir ifade zaten, değil mi? Yani bu da böyle.
Tamam.
Karıştırmasın. Okay. Any other question? Şunu sileyim. Okay, so if we define the induced norm of a matrix with this definition, there is one important property such that the norm of AX is less than or equal to the induced norm of that A matrix times the norm of the vector itself. Okay? And let's try to show that by using the definition of this induced norm. Okay. We want to show the norm of AX is always less than its induced norm times the norm of X. So, okay. So I will start with writing norm AX. And in order to pass to the definition of the induced norm, I will multiply and divide that thing with the norm of X. So X will be equal to divide by X times norm X. Okay. And I can write this if norm X is not equal to 0. Okay. If I'm not dividing by 0, then I can write that thing down. Okay. And notice that, so the first term over here is always smaller than, so I will write that smaller than, let's say, maximum value over all possible y vectors. I'm looking for norm AY divided by norm y. Okay, so I'll do it like this. So the first term here is always less than this maximization over there. And I can write down the second term over there, norm X, just next to it, okay? And the first term over here is, by definition, the norm, induced norm of the A matrix. And I have the second term as norm of X. So I can, by exploiting the definition directly, I can write down norm AX is less than or equal to norm A times norm X. So this is only valid for the induced norm of a matrix. So write that down. Induced norm of matrices. Okay. Let me show it. And furthermore, there exists a vector such that norm of A x star is equal to norm A times x star, and that vector might be not unique. Okay. And there is another example. So how are we going to apply the definition of induced norm in different choices? So this will be simply saying that it says that, okay, we would like to define an induced norm for n by n matrices, and the example says that, okay, choose the L2 norm in Rn and Rm. So I will define the induced norm of matrix in that case by saying that I am going to maximize the norm of AX, but that's going to be the L2 norm of that. while the L2 norm of the vector x itself is equal to 1. Okay, so it's going to be the maximize norm x is equal to 1, and the maximize that guy over here, right? Square root of ax transpose ax. So, and so what we will do at the end is that I have to find among all the vectors whose L2 norm is equal to 1, I will find the maximum value of square root of x transpose ax. Maybe I can write explicitly, for example, norm of x, if x is a vector, okay, that will be equal to the square root of individual values squared, right? So sum of individual values squared. So it's going to be simply equal to square root of x transpose x, right? That would be equal to here we did the same, so I want to write the norm ax, then it's going to be ax square root of ax transpose ax, then it's going to be x transpose ax. So I would like to find among all the vectors with norms 1, I would like to find the one which maximizes that thing, and I will record that number, and that will be my induced norm. Maybe I can show you the different geometric norm definitions as a visualization. So I will now switch to the slides that I prepared before. So 1 second, please. All right, so this was in the previous lecture, we were plotting the unit spheres in R square with different LP norm definitions, right? Okay, so I will go to induced norm definitions now. Okay. All right, so once again, I want you to concentrate on that. We are saying that, okay, choose all possible x's with norms equal to 1 and maximize norm a times x, okay? So what are the vectors whose norm is equal to 1? So they are the vectors that lie on the unit sphere with according to that norm definition, okay? And so in this example, I will consider all the unit vectors in R square, and this unit sphere can be defined in different ways, right? So we said that if that was a L2 norm that we are choosing, then the unit sphere is going to look like a circle, and we will traverse all possible x values, all these unit vectors there. And suppose we are given the A matrix, which is a 2 by 2 matrix in this case, is given like this. And this A matrix times x is corresponding to another vector, okay? So these are the vector x's with unit norm. And these are the A times x vectors, and they have different norms, right? And the induced norm simply says that, okay, choose the vector which has the maximum value of ax, okay, the norm of ax. And of course, this is done continuously, so I'm just showing on that grid, but this is done for all possible x's. So that's the definition of induced norm. So, but I can define let me pause for this or you're gonna be hypnotized. so I can define the unit sphere by using the L2 definition, right? So this is the Euclidean norm definition. So how does the unit sphere look like when I use the, for example, L1 definition or L infinite definition?
Diamond.
Exactly, it was a diamond and a square, right? So for the infinity norm, it was a square basically. And so these are the vectors which has a unit norm by if I use the infinity norm to induce, okay? And these are the transformed vectors a times x. So each one of these vectors, I still compute a times x. And then I compute the maximum value of those norms of the transformed vectors a times x. And in that example, if I pick all these unit vectors, possible ones, and if I compute the norm of a of x among all possible values, so the length of that vector is equal to 9, and the maximum absolute row sum of a is also equal to 9. So this is not a coincidence, but we will show that in our next lecture. Okay. So since it's 2:30 already. Anyway, so we can continue our example. So this times this is a 3 by 2 matrix. So we get 2 by 1 vectors and multiply by a 3 by 2 matrix. So we will end up with 3 by 1 matrices. Okay. So again, I will pick my unit vectors in R square, which lies on a square actually. And then I will compute AX, and I will get the maximum value of those, the maximum norm of those vectors, transformed vectors A times X. And it will look something like that. So I'm looking at all AXs. I pick the one with the maximum norm. And once again, which is not a coincidence that the AX infinity is 11 and the maximum absolute row sum of A is also equal to 11. So that was actually, so maybe I can stop the share and go back to our first norm definition. So share screen. Okay, so can you see the lecture notes now?
Evet.
Okay, so in the next example, what we will do is that if we choose the infinity norm for both in numerator and the denominator definition, then the induced norm of A is going to be the maximum absolute value of the row sums. But we will show that in our in our next lecture. So following that, we will start the concept of convergence. So after that, after showing that example, we will continue with the convergence of series. Okay, so I will stop recording now.